Let's get started with the second part of the lecture. There was two things I needed to do before we get to the applications of resolution. And one of these is how to convert to conjunctive normal form. It's a very simple procedure, but we need to mention it. Before I even do that, since we have this particular example here, I want to stress one thing because we didn't get to it. So remember, we mentioned this notion of a unit clause. A unit clause is a clause that has a single literal. Now, when you do a resolution like this, where you have 1 and 3, so 1 and 3, and when we resolved them, one of these was a unit clause like this guy. So in this case, this resolution step is known as a unit resolution step, okay? And in fact, I think everything we did here was unit resolutions. So I think 2 and 3, if you look at 2 and 3, again, this is a binary clause. This is a unit clause, but still that step was unit resolution. The reason I wanted to emphasize this notion of a unit clause and unit resolution, because actually this is a big deal, as we will see in just a little bit. But let me quickly now go over basically converting to CNF. Since resolution is typically applied to CNF and the guarantee of refutation completeness is applied to CNF, it's pretty important to see how we can get everything to CNF. You can easily convert any propositional sentences to CNF using the following steps. So I'm going to go ahead and list them and then give you a concrete example. So here's a step 1 where we basically remove all logical connectives, but this, and that. And then the second step, we push negations inside. And step 3, we distribute. And in this case, and then number 3, we basically convert to closal form. Now, this step, push negations inside, where we do the following rules. So if I have not alpha, that goes to alpha. If I have not alpha or beta, that goes to not alpha and not beta. And then if I have not alpha and beta, that goes to not alpha or not beta. And the distribution, so you apply this repetitively. And when you're done, when you have to keep pushing negation inside until negation appears only next to variables, right? But cannot appear next to compound sentences. And the distribute part is simply applying the following. If you have a pattern that looks like this, beta and alpha, then you will basically get the following. All right, so these basically are the things that you have to do. And we'll just take now an example. In your chapter, there's actually quite a bit of examples there. Here's one. Let's use blue for this. And I do have my delta is simply A or B implies C. That's what I have. And I want to convert this to basically closal form, CNF and then closal form. The difference in our terminology between CNF and closal form is just the use of the set notation. So step 1, we get rid of this connective. So we end up getting not A or B or C, all right? So we got rid of this. And now we only have conjunction, disjunction, and negation. And then step 2, we push negations inside. So we'll end up applying this rule here. And then we will have not A or, not A and not B or C. And that's it. So negations now appear only next to variables. And then step 3, what is our step 3? Basically, we need distribution. So we have this pattern here, and we want to apply it. So that ends up being not A or C, and not B or C, all right? And actually, we already have a CNF now. So this is already CNF. And if we want to do the last step of doing closal form, which is the set notation, then we're going to end up having not A, C, and then here not B, C. Okay, so this is a clause, and that is a clause, and this is our closal form. So we're done. All right, again, very simple steps. Straightforward applications of transformations, and this applies to any propositional formula can be converted to CNF and therefore to closal form. Now, of course, in some cases, it may blow up, and so you may have an exponential number of clauses as a result. I want to do one last thing here before we move on to applications of resolution. I want you to visualize something. And this is pretty important because it comes up quite a bit. And this is, let me show you a particular knowledge base delta, which has these particular clauses. We have A, B, not C, and then we have not A, D, B, C, D. But I want you to visualize what happens when you condition a closal form. So in this case, we're going to go ahead and condition on C, and then we're going to condition on not C. And look what happens. There's something you have to see very clearly because it makes a big difference. When you try to condition on C or on not C, you look at the clauses, they will fall into three categories, right? There is this clause. Well, let me well, okay. There is this clause which does not mention the variable or its negation, and those are unaffected. So this guy goes down as is. Now, and then there are clauses like this one, which mention C, right? The same literal I am conditioning on. What happens to this guy? This clause is B or C or D. When I'm conditioning on C, I'm setting the value of C to true. So what happens to this clause? This disappears, exactly. It disappears because it becomes true. So this is gone. Now look at this clause here. What happens to it? It has not C, the negation of what I'm conditioning on. What happens to this guy? So I'm setting C to true. That means this whole thing is false. So false or, right? So we remove, someone is saying we actually remove not C from it. Excellent. Okay, I want you to visualize this and remember it. That's what's going to happen. These kind of guys that contain the negation, you just drop this and take this. The guys that do not mention C or not C as is, the guys that contain C, the guy we're conditioning on, go away. Using the same logic, let's see what happens in this particular case. I'm doing not C, and now you have to tell me, I'll point to these three guys and you say drop clause, drop literal as is. What happens to this guy when I'm conditioning on this? What happens to this guy? Does it go down here? Drop clause, excellent. This does not make it. This goes away. And in this case, we say this clause got subsumed. Excellent. Now, what about this guy? As is, right? So this is, and now what happens to that guy? We're conditioning on not C, and people say drop literal, excellent. And then we get B and D. Very good. I'm doing this and in detail because when we get to SAT solvers and we get to a lot of the manipulations, a lot of the algorithm we're going to look at, they rely on this notion of conditioning to do their work. They effectively trying to intelligently use this notion of conditioning to simplify knowledge bases and recursive them. So this is bread and butter of almost all of the algorithms that we're going to look at later. And it's important to see what's happening on the knowledge base when you set a variable to true or you set it to false. Okay, guys, let's move on. We're already behind actually for today. And what we need to talk next about is applications of resolution. And again, so one of the private question about interaction between this and resolution, we're going to get to this actually. This is where it gets fun. Later when conditioning empowers resolution, as we will see. Okay, folks, As I said, we're running a little bit behind, but let's see how far we're going to go today. So this would be more of applications of resolution. And I'm going to mention 3 things. I had a different order for how to go over them, but then I'm probably going to go with a different order from the shortest to the longest so that we can make sure we finish certain things. So the first one I'm going to go over is basically existential quantification. This is one of the applications. The second one is simplifying the knowledge base. And the third one is deduction. This is the longer one. And what's going to happen is when we go over deduction, that gets us into the discussion that some of you brought up, which is what are strategies for picking up what things to resolve over. That gets us into the notion of resolution strategies. And there was one that we're going to talk about in detail. I don't know how much we're going to be able to do this today, and that's called directed resolution. It's not just I mean, it's special. It's not just a strategy for resolution, but what makes it particularly interesting is by the time it finishes its work, the things that it did, the trace it leaves behind, allows you to do many various things afterwards as far as obtaining information about your knowledge base. So it's actually pretty interesting. But let's start with the first one. And that's a pretty simple discussion here on the use of resolution to do existential quantification. So what happens here is pretty simple. Let me illustrate it with a concrete example. In fact, we looked at that example before. So let's say I have my knowledge base delta, and it happens to be A implies B, and B implies C. And if you recall, previously what we did was, if we wanted to existentially quantify B from delta, we did actually that according to the definition, which is take delta condition on B, take delta condition on not B, and then take the disjunction. And we actually found out that this gives us A implies C. So we forgot about the variable B, and that's what we're left with. So you can actually use resolution to existentially quantify in the following sense. And let me write this in a clausal form. So, or in CNF, that would be not A or B and not B or C. It's pretty simple. To existentially quantify B, or more generally a variable, do all B resolutions, then drop all clauses containing B, and more generally for any variable. So if you want to forget the variable X or existentially quantify the variable X, you go and apply every possible resolution over X, right? Any 2 clauses, one contain X, the other contain not X, you resolve them. When you're done and there is no more resolutions to do, you simply go ahead and throw every clause that mentions X. And that is basically the same as this guy, okay? So in this case, if we wanna apply this here, what can we do? Resolution over B, there's only one of them. I can resolve these 2 guys. And now what I'm gonna get is not A or B. Okay, these were the original ones. And then I'm going to add one of them, which is by resolving this, I'm going to get not A or C, right? I can't do any more resolutions over B. Now that I'm done, I will go ahead and simply throw every clause that mentions B, this and that, and I'm left with this. Okay, this was a very simple example, but that's basically the procedure here as far as doing one, which is existential quantification. And when we do directed resolution, which is a particular resolution strategy, you're going to see that when it's done with its work, one of the nice thing about it is, as I said, it leaves a lot of information behind. One of them, it ends up doing a lot of existential quantifications for you along this fashion. So you get the knowledge base projected on subsets of variables and so on. We're going to get into this. Okay, this is this simple part. The second part about simplifying the knowledge base is also relatively short, and this refers to unit resolution. So I'm going to say a couple of words on unit resolution, and we're going to revisit this guy quite a bit later because it plays a major role in systems like SAT solvers. So let me start a new page here and tell you a little bit about unit resolution. So we could have put this under basically unit resolution or simplifying the knowledge base. So if you remember what we said about unit resolution, is that it's a resolution step where one of the clauses is unit. So let's take a look at an example here. If you had, let's say, not A, B, and then you had not B, C. These are our clauses. And now let's say we have yet one more clause, which is A. Now, if I go ahead and resolve this guy with that guy, then actually to make it a little bit more interesting, let me do this the following. Let me make this E, and let me make this not E. Now, if you go ahead and let's say resolve these two guys, right, you're gonna get the clause B, E, and this is a unit resolution because this is a unit clause. If you think about what happened here is, what happened if you were to condition this on A, you would have gotten this as well. So conditioning this on A, it's like saying, I know the value of A is true. So if you know that the value of A is true, you're removing this and you're simplifying to that. Resolving with the unit clause A has the same effect. So because a unit clause is effectively asserting that A is true. So if I do this here, I get that. Now I take these two guys, then I'm gonna get this. And what did I infer now? I effectively inferred that B is true, right? And you go and do this with that, and then you get the unit clause C. So in a sense, when you're doing unit resolution, it's like propagating values of variables. And that's pretty powerful. It's like conditioning on the value of a variable. And therefore, sometimes people refer to unit resolution as Boolean propagation or simplifying a knowledge base. If you want to think about it from a resolution strategy point of view, a resolution strategy typically says, don't apply any kind of resolution, but when you're applying resolution, focus on these or restrict yourself to that. So you can understand unit resolution as a resolution strategy where do not do any resolutions unless they're unit. The problem with unit resolution, though, is if you restrict yourself to it and only do unit resolution, you lose completeness. So unit resolution is not refutation complete, right? So it's possible that if you just restrict yourself to unit resolution, it's possible that you will exhaust all unit resolutions and you have not discovered an empty clause. That doesn't mean that the knowledge base is consistent, all right? So it is not complete. Unit resolution is not refutation complete. However, what's nice about unit resolution is you can apply it in linear time. So if you have a knowledge base and you want to exhaust the applications of unit resolution, you can do this in actually linear time. Because of this, because it's so efficient to apply unit resolution, and because it could be very useful as far as propagating the values of variables, it ends up playing a major role in many systems, including SAT solvers, to the point where people have invested heavily in data structures for doing unit resolutions very efficiently. not only how to do unit resolutions, but how to undo unit resolutions. Because as you will see when we do SAT solvers, these solvers are basically like setting the value of a variable, then unsetting that. So when they set the value of a variable, they want to propagate using unit resolution. But when they unset, they want to undo that. So there's some very sophisticated things people came up with to do this extremely efficiently. So for now, what we need to know is unit resolution is very efficient to apply. Second, it can be thought of as doing value propagation and therefore simplifying the knowledge base. And third, it is not refutation complete. So it's not guaranteed to discover contradictions when they exist. Okay, yes, we now go to the last application, which is deduction. I'm trying to answer the question, does alpha logically follow from delta? Okay, so this is you can think of this as the knowledge base, and this is the query. And I'm simply want to know is, does the query alpha logically follow from delta? And we wrote this before as trying to answer this question. Okay, now you can't just use resolution to do that, because we have mentioned that resolution is not complete. So even though this guy follows from this, it's possible that you can exhaust the resolution and not find delta. So what do? You end up using two things. One is the fact that resolution is refutation complete. And second is this result we showed last time, which is called as the refutation theorem. I'm going to write it. And someone asked earlier about the intuition behind it. Well, the intuition is you know it. All of you know this refutation theorem, and you've used it. Refutation. So what does the refutation theorem says? The refutation theorem says alpha logically follows from delta if and only if delta and not alpha is inconsistent. So if you want to do this, what you can do is negate the query, add it to the knowledge base, and run resolution on this. So one of two things happens. If resolution discovers a contradiction, that means this is inconsistent, and therefore you know that alpha logically follows from delta. If you end up exhausting resolution and you don't find a contradiction, that means this is consistent, and therefore this does not follow. So let me spell them out. Here, outcomes. One, resolution finds contradiction on this guy. That means delta implies alpha. Then resolution does not find contradiction on delta and not alpha. Then this guy does not imply. That's simply. Now, to be able to do this, this has to be in CNF or closal form, right? So that means you have to take your knowledge base and then the negation of the query, everything into CNF, and then you run resolution, and that's the main application. Now, people started with this, and for a while, this kind of way of doing inference and deduction was given a lot of attention, and this is where all of these resolution strategies were discovered and so on. So we're going to do a quick example on this, but first I want to answer the question that people had on what does this intuitively mean? And someone actually put it nicely, said, how can I explain this to someone who's not an expert on this? And I already see the answer that someone wrote down. This is the technique of proof by contradiction that most of us have already used, even in perhaps high school. Someone says, prove that alpha follows from delta. What do? We say, assume not alpha. And then you ... and you get a contradiction. Said contradiction. Therefore, alpha does follow from delta. That's basically the refutation theorem. It's proof by contradiction. I want to prove something. I assume it's negation. And then I try to show a contradiction. Very good. Let's see a quick example here. What we have is this knowledge base. It happens to be A or B implies C. Okay, that's a very large bracket I put in there. That's fine. C implies D. And it has these two sentences. And alpha happens to be basically not D implies not A, right? And I'm trying to see whether delta implies alpha. So what I want to do, let me just make sure I got it right here. Yes. Now you may want to ask yourself first, the question is whether this is indeed the case. What I need to do is I need to take delta and not alpha and convert to CNF or closal form. And we're not going to do this here. I did that. And then when you take these two guys, they will end up being the following clauses. So I will have not AC, and then the other clause is not BC, and then I will have not CD, and then I will have not D, finally this. Now, if you look at these clauses, you'd see that part of them are coming from delta, these guys, and these guys are coming from not alpha. The nice thing about converting to CNF is you can convert delta to CNF and convert not alpha to CNF independently and just paste them together. So this is what I have. I have 5 clauses in this case, and I want to see if I can get a contradiction. And if I get a contradiction, then I have proved basically that delta entails or implies alpha. Well, let's do it, guys. So let's see. Yes, any suggestions for, give me numbers, 2 numbers of clauses that I need to resolve together. People said 1 and 5. Let's see what happens with 1 and 5. I'm resolving over A. I'm going to get the unit clause C. Let me see. Okay, we'll go with the next suggestion, which is 3 and 4. 3 and 4 we can do on D. Oh, wow, that was easy. 3 and 4 on D. So I would get not C. And okay, a empty clause. And that is 6 and 7. Done. So what did we conclude? We concluded that delta does imply alpha. Okay, it's pretty nice and simple. Now, you will see in your chapter other examples. In particular, you will see examples where you will not get contradiction, but instead you exhaust all possible resolutions, and then you know that it's consistent, and therefore you could not get a contradiction, so alpha does not follow from delta. Let me say a word on resolution strategies, and it looks like we have to defer the discussion of our main resolution strategy called directed resolution till next time. Now, the resolution strategies, let me end with this here. Okay, let me, before I make my remarks, I will put down an example that I'm gonna refer to. Well, let's color things a little bit. Okay, so resolution strategies are restrictions on resolution, simply stated. So if I don't constrain you, in principle, you can pick any pair of clauses that can be resolved and then resolve them. Resolution strategy says no. Listen, to make things efficient and maybe get to your objective, how about you follow the following restriction on how you apply resolutions? The first question that comes up when you talk about a resolution strategy is, are you losing completeness? So is the restriction or guidance that the strategy gives you, would it prohibit you from discovering a contradiction if one exists? Some resolution strategies lose completeness, and we just saw an example of that, which is unit resolution. It's fast, but it's not complete. But still, people found excellent uses for it, and we're going to get back to this later. And some are complete. I'm going to mention one very briefly now, which is complete, because it will allow me also to introduce another concept. And next time, we'll talk about yet one more complete resolution strategy, which is what I mentioned, directed resolution, because it has very nice properties and very human-friendly and guided. You don't wander around. Directed resolution. Okay. The thing I want to mention now is a resolution strategy which is called linear resolution, and there's a whole bunch of them, by the way. In your book, in your chapters, you have an exposure to some of these. So linear resolution, and this is a particular strategy. And to explain this, we want to do a resolution trace, not as we did before by numbering things, but by doing something like the following. And I did this earlier already by building a graph. So in this case, I'm saying I'm going to resolve this with that. And then I'm going to get C. That was a unit resolution. And then I'm going to say, how about I resolve this with that? And then that's a D. That's also a unit resolution. Resolved over C. And then how about this and that? And then I'm going to get C. I resolved over D. I got not C. And finally, how about I resolve this guy with that guy? And then I'm going to get the empty clause. Done. Okay. This, what I drew, is known as basically a resolution graph. Now, I wanted to illustrate this concept of a resolution graph, but also it happens in this case, the notion of a resolution graph allows us to state nicely what is this linear resolution strategy. So linear resolution says, anytime you want to resolve two things, all right, and let me write this for you, and resolve C1 and C2 clauses only if one of them is root or an ancestor of the other. Okay, you can only do resolutions between C1 and C2 if one of them is root in the resolution graph or is an ancestor of the other clause. Well, let's see, is this a linear resolution? Does this adhere to the linear resolution strategy? We did, let's number them. We did 1, 2, 3, 4 resolutions in this case, 4 resolution steps. You have to check them one by one and see if each one of them adhere to this restriction. If you look at the first one, both clauses were roots. Now, what does it mean to be root in this case? Root means it's in the original knowledge base. So if you look at this guy, both of them were roots. So this is good. Let's look at the second one here. There are 2 guys that I resolved, and one of them happens to be root, right? That satisfies this condition. So that's also good. Let's look at the third guy. Again, one of them happens to be root. That satisfies the condition. Done. Now, if you look at the last one, no, neither is root. This is not root. That's not root. That is, these are not original clauses in the original knowledge base. So now I have to make sure that I have the other condition, that one of them is an ancestor of the other. This is an ancestor of this. See, this came from that. So now I satisfied the condition, and therefore this actually worked. And this is what's known as a linear resolution. It's called linear resolution also because when you look at the resolution graphs, they look like they're a chain. Like linear resolution will come up actually later also in the sense of SAT solvers. But the question now that you have to ask me is, so is this complete? Does this remain to be refutation complete? Do I lose completeness if I restrict myself to linear resolutions? And it is complete actually. So unlike unit resolution, this resolution strategy, linear resolution, is actually complete. So that's an example of a strategy. Of course, when people suggested these, and there's so many of them, they had justifications, and when they would focus the resolution process and so on. We're left in this chapter 2 with one resolution strategy. As I mentioned, let me write its name again, directed resolution. In fact, about quite a bit of the chapter is on that one because it's pretty special in many ways, including historical. That's something we're going to go over next time. I think that's, we're done. We don't have much time. Thank you again, and I will see you on Thursday.